Okay, my friends, listen up. This is Roger. This is about the G2 experiment looking for muons. And we have to rewrite the physics books. Listen to what he has to say. And this is called Muon Experiment. Did scientists just discover a new force of nature? DW News. That is the one that put this video up. Now listen to this. It's very important.
Physicists are excited, and they say this could be a major breakthrough in our understanding of the universe. It all has to do with the behavior of subatomic particles called muons. Experiments at a lab near the U.S. city of Chicago have shown that muons move at a rate that's faster than expected, potentially unlocking the secrets of a previously undiscovered fifth force of nature.
This could be the door to a whole new world of physics. For years, researchers have been using this ring, made of superconducting magnets, to accelerate the tiniest building blocks of matter, called muons.
Okay, this is where I disagree with what they think they have done. I believe they are accelerating electrons by themselves up to virtually the speed of light. Let me show you why I make these statements. But let it continue on for a second, and then I'm going to talk about our experiments and us actually seeing the muons. Okay, so here's what they're doing at Fermilab. They're speeding up these particles. Now, I'm not going to say what kind of particles they are, and you make your own decision, but I will show you what I think they are. Now, let's listen to what he has to say.
Interact with other forces and particles. And the results show that muons actually behave completely different to how current theory says they should. Up until now, something called the Standard Model explained all subatomic particles and their characteristics, such as charge, mass, and lifespan. But scientists have observed that the behavior of these muons suggest particles and forces exist outside of this theory.
That literally is what it should look like. That is what the nucleus does look like. It's a batch of particles that all you can see is the whiteness of them. The darkness of them is inside. We've never seen the dark matter. I will show you the dark matter because we brought it out by accelerating light, which also is not supposed to happen.
Everything that we can see in our universe, everything around us, can be explained by a few building blocks. These blocks describe the Standard Model of particle physics. One group of these particles makes up matter.
All right, I'm not going to go any further at making up matter and antimatter and quarks and all these different things they talk about, because here is literally what everything is made out of right there is electrons. Nothing exists other than electrons. Now, in mass, they become stable as molecules and atoms, and a proton's worth of electrons is 1839, I believe. So there's 1839 dipole electrons in a ball would be one proton, instead of one big gigantic positive. All right, so that's what what they're doing in CERN and all these other places. They're smashing particles together, and they get debris coming out of their ears, billions of bits and pieces, and they dig through it, and then they find what they'll end up finding is a bunch of different particles. Some of them will look like that. Some of them will look like this. Some of them will look like crazy-looking things, and if they find enough of them, they will say, well, that's a subatomic particle. So then they have quarks and leptons and muons and fermions and phonons and photons, and I mean, it goes on and on and on. But every single one of them is made from an electron. And an electron is what we always thought was electricity. Well, it doesn't have just an explosive, pushy part. It has a black matter part, a dark matter part, a muon part, an attractor part. Here is exactly what an electron looks like. This pushes and shoves. This doesn't do anything. All it wants to do is attract a white particle to it, or green or blue or red, whatever the particle is. But I'm going to show you what this is in light experiments, because we did the experiments. These are the photons, nothing more than a bar magnet back to back, and an electron is nothing more than a bar magnet. They just never saw the positive muon dark matter side before. They know it exists, they just never saw it, and you never will see it, because everything there is crusted with the electron portion. They want to push away from each other. The muon portion wants to pull them all back together. I'll show you this, and it's very hard to dispute what I'm going to show you. And if you can, I'd like to discuss it one way or the other. All right, now they think they've come up with some very precise calculation to make it fit into the standard model, sort of, but they realize it's just not working. So listen to what he has to say here. And read between the lines, because they realize it's not working, so they're sort of just trying to force it into the standard model, and it doesn't work. Here is the model, the electron flood model. Nothing but electrons exist. Now listen to what he has to say.
To an extreme likelihood that there's something about the fundamental structure of the universe that we really don't understand. And if that new measurement and this discrepancy between the two would stand up and would stand the test of time, it would be proof that there's something missing in the model of our building blocks of what the universe is made of.
Exactly, something in the building blocks of what the universe is made of. Every time they find a new little quasi-particle, they call it, it has a different spin, it's spinning up or it's spinning down, or it's wobbling, or they have all kinds of different little signatures that they say, okay, there's a new particle because it's doing this, there's a new particle because it's doing that. No, it's all the same particles, they're all electrons, and they configure in all kinds of different ways. I will show you in our light experiments, but let's finish up with what they have to say on the cutting edge of science. Here goes.
And now this could be a new force, like you said in the intro, it could be a new particle, but it will in general influence the universe around us and all of its contexts, including muons, and in that sense will define a new paradigm in how we look at what the universe is made of.
Could you hear him talk about the muons? That's exactly what I'm showing.
Could it possibly help explain some of the biggest mysteries in the universe?
Let me just say this, it explains every mystery of the universe. 100%, I'm going to tell you right now, if you can come to me with anything whatsoever, any interaction, anything, I will talk about it and we will discuss it, because I'm going to tell you right now, carbon dioxide is not the problem with our atmosphere. It's the scrubbing of the outside surface of our ionosphere with all the other particles of light that's in the vacuum of space, which is not a vacuum. So as we scrub through it, it's 2,700 degrees way out there, 100 on the surface. That's the only reason it's 2,700 out there. And the same thing with the sun. The sun on its surface is 7,000 degrees. You say, ooh, that's pretty hot. No, it's not, because the corona is millions. That's way out here where its atmospheric discharges are interacting with the scrubbing through space. And we're all tunneling through the universe on the arm of the galaxy, Milky Way, and spinning at the same time. A lot of electronic interaction, push to shove. All right? And they don't understand it because they've lost the concept of thinking. You have to understand space is not a vacuum, first of all. There's so many things that have been taken for granted that pollute the end result, that all it is a bunch of trying to figure things out that can't possibly be understood because they don't make sense, because they never started from the correct spot. Now listen to what he has to say. He's already said this is going to be new physics, basically.
Yeah, so there are several big mysteries that most physicists agree that are present and we can't explain. The largest being that we don't really know what 95% of our universe is made of. We know that 70% of it is made of something called dark energy, which is what we use to explain why the universe is expanding at an accelerating rate. And there's also the other 25% is dark matter.
All right, and that's exactly what I'm going to show you, the dark matter attached to the electron.
And we know that the dark matter has to be there because it influences parts astrophysical parts of the universe when we look out to the stars, but we don't know what that dark matter is. And it could be that should this result from the muon G1s2 experiment in Chicago be proved to be a new physics discovery, that it could be that source of dark matter that as of yet we haven't found.
Well, let's say that the numbers are in your favor and that this discovery turns out to be real. Are we going to have to rewrite the physics books?
Well, yes and no. I mean, the standard model that was described in the intro works very, very well and describes a lot of the universe around us, and we can do tests and show those to be correct. But it's still true that if this result was to stand up, it will be something very fundamental about the structural universe, the structure of the universe that we haven't yet observed.
Exactly. Let's just cut to the chase. They're trying to create a model based on all of these different little bits and pieces that they can see, because they're smashing globs together and they're seeing all these pieces. Yes, they're going to see a lot of electrons. They're going to see a lot of muons. They're going to see a lot of electron showers. They're going to see a lot of photons. They're going to see a lot of bits and pieces, which are nuclear bits and pieces, and they're going to try to attribute them. Sometimes they're spinning up where the black ball is down, and sometimes they're spinning down where the black ball is up and the white ball is down. And I will show you all this right now. Let's just look at the experiments that will cover all this stuff. And we have new physics, and we need to start looking at it today, because I think it can create free energy. And I'm going to show you why I say that. All right, if you're really interested, I'm going to be getting deep into this, I'm sure, later. But this is just a taste. This is laser light. This is laser light accelerating. When light accelerates, that is not allowed in the physics world. That is laser light accelerating. This is the particle. It's called a 2p2h particle. That means the 2 p's are the white spots. Those are particles. And the 2 h's are the holes. This is what you need to create muons. These are, and each side of this is a neutrino side. So this is a muon, electron neutrino, and a muon neutrino. And basically this is just exactly what you have. The black part is the muon, the white part is the electron. Back to back, they're just nothing more than 2-bar magnets, and they explode at the venturi, which is right here, and they actually divide into bits and pieces, exactly what CERN wants to see for their muons and electron showers. Alright, here's what it is. These are muon neutrinos and electron neutrinos. There it is right there. The muon neutrino, the black one, electron neutrinos, the white one. When they come forward and smash, they're high power particles, high energy particles at this point. When they smash into another medium, it's what's called Cherenkov radiation. The white one forms a shower. You see it? The black one just keeps going on its way, but they separate. They know this happens, they can see it, but they don't have any idea what it started as was an electron. And that electron, back to back, if there was 2 of them back to back like that, it's a photon. As I showed you before, the black and white balls attached together. And here's what we did. We did it. Here it is right there. The black ball separated from the white. The blacks come around the outside and reattach out here. This is light, so the speed of light is pretty damn fast. So they broke apart here, fission. They fused back together here is fusion, and that happened within that distance. And this venturi is tiny, tiny, tiny. It's very tiny. This is a blow up of it. So it's that's power that just is unbelievable. And as you can see, just visually, think of this visually. That's like an explosion of atomic energy, and it really literally is, because that's fission when the particles divided, and that's fusion when they came back together. In between is raw energy, and that's light accelerating. So we got a lot of problems with Einstein, Hubble, the space expanding, all of that stuff. All of that. All right, we're going to go over this particle in a moment, but we're talking about neutrino, which is what I've been showing, neutrinos, muon and electron neutrinos. their interaction as generators. Now listen to this very carefully. We have to understand the so-called two-particle, two-hole effect, the 2p2h particles I'm going to show you or have shown you. It's urgent program in neutrino interaction physics for current and future oscillation experiments. Oscillations are the flipping around. Such processes are believed to be responsible for the event excesses, that's free energy, observed by recent neutrino experiments. We did this, and then we went ahead and we could see these particles actually dividing. And I show you, or have shown you, so let's get into it. Now you see that? That's the photon. It's the 2p2h particles. Two particles, two holes. And this is just as it's concussing. It has its spikes sticking up. And it will explode and divide. The whites will fly off and the blacks will just go around. The whites will turn into showers. Now, I have them in the red as well, and it's a little better. I can show the progression. All right, here they come in. Light comes in. You would never see anything at all here. It would be just like up there, dark-ish. And then all of a sudden they start to glow. Well, they're glowing because they're concussing, stacking up at the venturi. Then they pile up here and they start to box up. You see, they start to box up. And then they get really very glowy and spiky. They have a spike coming out of them because they're getting ready to pop apart. And then just like popcorn, there they go. And they go flying off. And what goes flying off is the black and the whites separate. And the white goes through its venturi and creates showers. And the blacks won't go with it. They go around because they're just too big. They're too, and I'm going to show you these particles in extreme close-up. But they won't go through, and here's what happens at the end. Is you have the black balls all congested around the outside and coming around the outside and then reattaching over here as the white ones drag the black ones, or the black ones drag the white ones back in. The black ones are extremely big compared, or extremely heavy, or extremely attractive. Call it whatever you will, but I'm going to call it dark matter. Never been seen before, except by CERN, and they didn't realize it. They just said, ooh, that's a muon, or ooh, that's a boson, or ooh, that's a fermion, or whatever they want to call it. But it was the particle that separated from the four-banger. All right, we saw it. No reason to believe that that's not the facts. There's the light coming in, there's the four-banger, there's the explosion. And that's when they turn into their muons and electron showers. And that is exactly what CERN wants to see, and is exactly what we presented. And that's it right there. The muon neutrino, the black ball, the electron neutrino, the white ball attached together. But there's a four-banger. Now, separated is just an electron. So normally you would have this as a photon. These will bounce off of you because they're semi-neutral. You know, well, they're pretty much neutral. There's two particles attached back to back like two bar magnets. They satisfy that neutrality. Any single particle is aggressive. They're called charged particles. When you get down to the electron region where you only have one particle, they're aggressive as hell. They are aggressive as hell. That'll burn right through you if there's enough of them at one time hitting you, and all they are is electrons. If they're just flooded with light hitting you, it's a whole different issue. Then you're getting hit with a ton of these. And they will all sort of bounce off you. They'll warm you up, yeah, but they're not going to electrocute you like the electrons will. If they're all strictly electrons, right into you. Directly into. They want to fuse with something. That's the difference between light, which is a neutral particle. It'll warm you up, it'll light you up, it'll glow you up, but it won't explode you and incorporate into your tissues like the electrons will. Fully understood. All right, now don't forget, this is a single slit, but it's a venturi. And I can explain that, and there's a certain width and a certain this and that you have to have. But it's not a pinhole venturi. That's the mistake people are making. This is spinning light. And because the venturi is straight up and down, you can actually see the spin through the venturi. It's quite obvious. Anybody that's a machinist can see that that is a drill bit. That's a drill bit. And it's turning to the right and spinning through that slit. And as it does, the particles are spinning because that's the way light works. I just showed you the Majorna electron spins. That's what they spin. Now, as it comes through the other side of the slit, they are so energetic, they don't want to be next to each other, so they push and shove, push and shove, and push and shove. Is what creates all of these different interference patterns. This is a single slit. It's not flapping a wave and this and that. So think about that. And all this was done with this exact foam and this exact red laser, a construction laser. And I don't have any idea how much, it doesn't take much wattage. There's only 2 AAA batteries in here. So it doesn't put out much wattage, but boy, I tell you, when you see the energy increase, it's unbelievable. And Rod did all these pictures. I had the same equipment he has. He's in Australia, I'm here in the United States. But he must have spent thousands, literally thousands of hours. You know, I worked with him for 6 years, 7 years now. And he still uses the same Galaxy S3 Samsung phone. As a matter of fact, I was just talking with him today. And he says it's just a fabulous phone. It just has it picks up everything. Now, I know he's got a whole bunch of other stuff he's used in the interim, and he's got different lasers and so forth. But this right here is all from this, right there. Everything I'm showing you today, except for the green one, that's just from other green laser. But it's all going through 2 tiny little finishing nails, literally through 2 finishing nails, virtually free. So if you could do that, but you got to put them so close together, and then you got to put the laser hitting right into the center of them, not too far away. And then on the other side, he was taking this, using the selfie, and going right down and pew, 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 taking pictures, and I guess right into the front of him. When I saw what he was doing, I just said, "Rod, you just go, brother, go." And I do the atomic part. He's not into the atomic part at all. He's an experimenter. He just did it for his own pleasure. And when I saw what he was doing, it freaked me right out. And I went right off the charts, man. I was off the and he was so gracious to be so accommodating. He never made a penny on this at all. And I have never even made a penny on my stuff either. I just want to make this understood that we can get free energy right now. And when I say I never made a penny on, I get paid some from YouTube. It's not a ton, and it goes to good causes. So let's see what this is all about and how we can get free energy. I'm showing you the particles, I'm showing you the accelerator, I'm showing you the raw energy, and let's see how we can harvest it, I hope. All right, you see this? This is unbelievable. This is looking right into the venturi, so the light is coming out at us. You see these white spits here, where there's nothing in there but white? And it's sort of a blank area, just these white particles coming at us. And then all of a sudden they turn into these circular disks. These are Higgs fields. And what you're seeing right there is a reverse spinning particle. I'm almost sure of this. Because again, Rod did these experiments, and I got the aftermath. He just would send me pictures, and then I'd have to go through them and try to figure out what was going on. And I'd ask him questions about it. I said, well, how'd you do this? And he said he took a shot at it where the light was coming right at us, and he picked this up. And I saw this white particle, and I said, whoa, what the hell's going on there? Because they're all these Higgs fields, 100%. They're everywhere, 100%, except that one. Then I found this other shot, and usually what he does, he takes a series of things and then sort of ferrets through them, I guess, you know. And I don't work with Rod, and Rod is a man of very, very, very few words. You know, I had to drag everything out of him, to be honest with you. He just loves doing this stuff. And it's just fabulous what he does, absolutely stunning. And I took the time to examine them carefully and say, well, how did this get purple? Why is that purple? These are red. These are all supposed to be red. How's that purple? Why is that orange? Why is that a white spot? What the hell is going on? These are all supposed to be Higgs fields. And normally they are. And then I saw this come along. Look at that. I think that was that white particle. And I think it had characteristics of Higgs within it, but it was spinning backwards. Is all I can take from this. And it hit this field and spun off what I call a light trumpet. I don't know what to call it, but it's certainly not a Higgs field, which is what we would expect to see at this point as the decay of the particles. So it's not that, and it's not an electron. I don't know what it is. It's one of those things that's a mystery, but it's a deep, deep mystery now, because I thought I was at the point where I could say, yep, absolutely, we got the muon and we got the electron shower and the electron neutrino. And that's the basis of everything. I was there, and then I saw this. I said, yikes. All right, what you're going to see here is the green laser at the top. You see how concussive and powerful it is? The red laser's at the bottom, having two lasers going through at the same time, through the same slit. And a slit is just like this. It's going through that tiny little venturi, and it's just, that's all it is. And you can see there's some red ones up here. See little reddish looking spots. These are the green photons, just like before. All right, blue is extremely powerful. You can't see the particles easily. You can just barely make out that there's two little bits to them, the two whites, but they're spinning so fast that you really can't see it. But you can see that they're tight here and expanded here. So it's either slowing down or speeding up. You take it for what you want, but I can tell you one thing for a fact. That one there is changing its speed, and this one here, there's zero question that it's not accelerating. That is accelerating. If light accelerates, Einstein was wrong. And if light accelerates and light can slow down, because all of the particles in space are these particles that I showed you, and they're light particles, light is slowing down coming to us. We're not expanding out faster than the speed of light now. All of that stuff has to be reconsidered. Hubble's not right. Bohr wasn't right. Einstein wasn't right. Until you decide to look at electron flood theory, nothing will ever make sense. All right? Look at this, and then if it's wrong, it's wrong. If it's right, it's right. But I say everything's made of electrons, and that solves 100% of everything. It covers the blue sprites, the red sprites, telluric currents, all the things that nobody talks about because they can't deal with them. There's no way to deal with gravity even. They drop something, they don't even know why it hits the ground. And that's because the standard model can't account for it. It can't account for if light is a particle or a wave. It just doesn't, none of that stuff. Nobody is in concordance about that. Right now you can see what you can see. And if you can't see it, I don't know what to say. But that's what I hear from the top physicists. Oh, no, that could be anything. That's just screen, this and that. And within 5 seconds, it's dismissed and they're gone. And trust me, I understand this pretty good. And this needs to be investigated. And if it's right, the end result is this right here, and it's free energy, and we can fix the problems of the world. Because that's the only way we're going to get out of the problems we have right now. People have to be able to stay in their own countries and have free energy to grow food and drive around and heat their places and cool those places down, clean the water. All of that stuff can be done basically for free. This is the most inexpensive equipment that you could possibly imagine. We use the laser and the CMOS collector. This is it. This is all you have to do. And then you feed it down. It's, a little engineering, but very simple. And I believe this can be done. So, that's what I'd like to see. And I showed you this is fission, that's fusion, this is a hell of a lot of more energy than we started with. So that's what I'm going with this. And if anybody wants to get involved, I'd certainly like them to, but I need to be involved as well. Because I had somebody try this, and they used pinhole Venturi, and that's not what we need. We need a slit Venturi. And I can explain exactly what that is, and it's not, I don't think it's what they did. So, and if they don't get the neutrino, if they don't get this interaction, it's never going to happen. It's not, and they have to be able to look at it and see, am I getting it or am I not getting it? And Rod would be the guy to talk to about that. I don't know if he's willing. He didn't seem to be too interested in going too much further with this, but you know, I would hope maybe he would. If somebody shows interest, nobody's ever has. So we're hoping that it's sooner or later going to happen, because if we can create free energy, the whole world will change literally overnight. People won't be attacking our borders. You won't be trying to go steal somebody else's resources. We won't be burning coal and oil and gasoline and all that stuff. And you know, it'll be a little disruptive, absolutely. That's the way life is. It's not going to be that bad. It's going to be nice, because there'll be so much extra work to do, because the energy will be free. So I'm going with that. All right, just to recap, straight laser light, that's all it would ever do, is be this fast, and it would never exceed this speed. However, the Venturi forced it to accelerate. Then we could see the actual particle, which has a magnetic field around it, a very large magnetic field. It's going through the gases that are out in front of it and concussing with them, creating this wave. It's the field that surrounds the particle that creates the wave. So these glow as well. All of the particles in the gases have to concuss, and they glow according to how hard this is pushing. All right, that's why things glow brighter the harder they push. Now, this is going through the Venturi, and we can see something's coming out of there. And I know what's coming out of there. This is coming out of there, that particle. And you don't see that particle. You would never see that particle at all. You would see no particulation whatsoever unless it hit this Venturi. You see up here? There's nothing there. There's nothing there. And the reason there's nothing there, there's particles up here. See them all over the place? They're all everywhere. There's light particles everywhere. But they are not interacting. But here, they're being pushed back. This is reverse EMF, all right, electromotive force. Coming forward here, it's hardly glowing at all. You see up here, look, how much is that glowing? Not glowing much. That's laser light. That's about as intense as you can get, hardly. But it's not glowing anywhere near this. Look at this. So what did we do? We made it hit a Venturi and just literally explode. And what did it do at that time? It's created so much reverse energy that is lighting up the faces of these. See, this is a face. That's a face. There was just, the whole thing is here. This whole thing is here. You're just never going to see it because it's not concussed enough. This is blowing back so hard that it's making that glow like sunlight. Just think of the energetic value here. Look at just even around here, the intensity of the glow. It's absolutely phenomenal. All right, so anyway, we got some serious energy that we're going to be able to use. Now, we got, let me find here we go, somewhere down here. Photon colorized. So here we got the photons. We know these are photons. 2 holes, 2 particles. Electron, electron. Bar magnets back to back. Flowing through the air, that is what would be called downspin, because the leading edge is glowing here. And that's the downside. When that charges up, and it will charge up, it'll take an instant in time to charge up, because what is happening is, you see it going this way? This right here is hitting all kind of particles in front. You don't see them, but you can see them here in the however they enhanced this. I didn't do this, but I know exactly what it is. It's an enhanced energetic representation of this. And that is going forward. This isn't faked. This is exactly what this is. This is not any different picture. This is enlarged and colorized, and it's showing the energetic values of these particles. If you look really carefully, you can see this is a glowy one, and that's not nearly as glowy. So that's what's happening. And this glowy one is real glowy because it's banging into all these little ones that are in front, those gas particles, like I said. Now this is the upspin. This is, well, yeah, this is a downspin. So when this charges up so much in a couple of, well, instants, that it wobbles and flips. And then that brings this one in front, and this one will be in the back to discharge. This one will start to concuss, and it'll have all little particles in front of it. And then as it charges up enough, it wobbles back, and this pops up in front again. That's what they call a muon wobble. Well, I agree with that. But they don't realize that's what's happening. That is what's happening. It's push to shove. Push, and these are shoving back, and it keeps getting hotter and hotter. It says, oh, pow, and then it flips, and then that one goes in the front. And it's just push to shove. Everything there is that is energetic, that creates any form of energy whatsoever, is an electron interacting with another electron. That's all there is. You go like that, and you have heat in your hands, it's push to shove. You're pushing one of these against another particle. All right? Anything that bangs in, that I could feel that slap my hand. That kind of stings a little bit. That's push to shove. Light is push to shove. Electricity is push to shove. Everything is push to shove. This is another particle they've seen and they don't understand, but we see them all the time. See, they are right there. And they come spinning down. Light is a spinner. It's not a wave. It's not a bouncer. It's a spinning particle. And let me show you that. Okay, this is Fermilab, and they're looking for the particles I'm showing you, and I've been blocked from being able to communicate with them because I showed them and they really laughed at me and blocked me. So if anybody can help get this through to them, we're looking for muons. I just showed you the muons. And you know what happened was they said they won't look at anything I have to present to them because I'm not peer reviewed. And I says, I can't get peer reviewed because I'm not published. And they said, well, then you have to get published. And I says, they won't publish anything because I'm not peer reviewed. They don't want to see what I have to show. The peer review process stifles any kind of information like this. So you got to help me. Somebody's got to stand up. I'm blocked. I can't get through to anybody, not a single person. Okay, the next video is going to start with phonons. In physics, it's nothing more than a particle of heat. A phonon in condensed matter physics is a unit of vibrational energy arises from oscillating atoms within a crystal. They're saying that it's shaking, so it's forming heat. I say no, it is an actual particle. It's not just a shaking which causes the heat. A particle comes and it creates heat. A particle leaves, that's cold. You take the particles out, it gets cold. Absolute zero means there's absolutely zero extra electrons. Every single one of them has been taken out. So when you hit that with electricity, instantaneous, it's a superconductor. But instantaneously, it starts to oppose the conduction. You have to keep it at that temperature, and you can't. You cannot harvest any extra energy from that because the energy coming in is just nothing more than heat. So you can't stop it. It's instantaneous. As soon as you hit that absolute zero conductor with any electricity, boop, it's done. It's over. All right, so like I said, the next time around it's going to be about these phonons. This is MIT. This goes back quite a ways. They just dropped the ball on it. And this is what is real. These phonons are real. And here they are down here. It says, in a sense, a phonon is a fancy word for a particle of heat. And a particle of heat is nothing more than an electron. All right? They go in, it gets hotter. They come out, it gets colder. And I did this, and I can prove this with the weight of things. Do you know that if something like this rock here, which happens to be a goose, by the way, if this got hot, what do you think would happen to it? Would it get heavier or lighter? All right, the hotter it got, would it get heavier or lighter? Well, guess what? It'll get heavier. It doesn't float up because it gets hot. The only thing that floats up is gases because they expand. They take up more room with the same amount of molecules. The molecules here are not going to go away. They're going to accept more electrons, and electrons have a weight, and this will weigh down. And I can tell you something that happened to me long ago. I was in the electronics business, and we had scales, and the scales had to be calibrated, and we had weights that had to be verified every so often by the weights and measures. And I took them up there when they were cold. And the guy says, you have to leave them. They have to warm up to room temperature. And I said, why? What's the difference? Why is that? And he says, because they won't weigh right if we weigh them cold. And I said, explain that to me. And he says, I can't explain it. We just know it happens. And now I understand it. Because cold means there's not enough electrons in there at room temperature. You have to be equal in the temperature here and the temperature here have to be the same, so you have the same number of electrons. One of them's not trying to flow out against the other. That's what it's all about.